Right, we'll go ahead and get started. So I'm here to present Dr. Michael Tallman, Assistant Professor of Math Ed at Oklahoma State. Michael Tallman received his Bachelor of Science and Master of Arts in Mathematics from the University of Northern Colorado, and he received his PhD in Mathematics Education from ASU, Arizona State. Dr. Tallman has taught mathematics at the secondary and post-secondary levels. His primary research is in the area of mathematical knowledge for teaching secondary and post-secondary mathematics. Dr. Tallman's work informs the design of teacher preparation programs and professional development initiatives through an investigation of the factors that affect the nature and quality of the mathematical knowledge teachers leverage in the context of teaching. In particular, his research examines how various factors like curricula, emotional regulation, identity, and teachers' construction and appraisal of instructional constraints mediate the enactment of their subject matter knowledge. So I will now turn it over to Michael.
Well, that was half of the talk. I'd like to start by thanking Irma and the rest of the graduate students for the invitation. It's been a really enjoyable day, and also to the faculty for inviting me to attend research groups and classes. I really enjoyed my day. As Irma mentioned, my research is about investigating the influences that mediate the enactment of secondary and post-secondary teachers' mathematical knowledge. I'm going to be talking about the first study that I did in this area today, and I hope in the hour after the talk I'll have the opportunity to talk about some things I've been doing more recently. This is the study I'm talking about today is a study that really led to a hypothesis that I'm currently exploring in my research, so I thought this would be an appropriate thing to talk about, especially for graduate students. So these are the research questions that I explored in this particular study. First, what are the influences that mediate the enactment of secondary teachers' knowledge of this particular content was sort of inconsequential, but I focused on angle measure and trigonometric functions for an in-service secondary teacher. And also I looked at the effect of these mediating factors on the quality and coherence of the meanings the teacher's instruction affords students the opportunity to construct. I'll focus most of the talk on this first research question. So to give you some insight into the experimental context here, I was working with an experienced secondary mathematics teacher. This individual had 13 years of school teaching experience, had just applied for his national board certification and received it. He was regarded by his colleagues and his administrators as an exemplary teacher, and I identified him because of his exemplary mathematical knowledge in particular. He was a graduate of a master's program in mathematics at Arizona State, and I had the opportunity of working with this individual in the context of his master's courses. As I mentioned, the context for the study was trigonometric functions. I focused primarily on angle measure. As far as the experimental methods, this issue of identifying the influences that mediate how teachers leverage mathematical knowledge requires the construction of multiple models. One of those models is to understand and to get a sense for the teacher's personal mathematical meanings. And this is achieved in a clinical context. I conducted a series of task-based clinical interviews. I also constructed a model of this teacher's enacted mathematical knowledge. This is a more difficult model to construct because you're collecting it in the context of classroom practice and lesson planning, and as a researcher you have fewer opportunities to intervene and to probe the teacher's thinking. So relative to this model, the way I approached getting a sense for the teacher's enacted mathematical knowledge was simply to characterize the mathematical meanings that students had the opportunity to construct through participating in the teacher's instruction. After I constructed these two models, I compared them to identify discrepancies. Are there moments when the teacher is promoting mathematical meanings that differ from those that he demonstrated in the clinical context? Are there things that are more sophisticated, less sophisticated? And then I tried to identify the potential role of mediating factors on these discrepancies. I'll go through this somewhat quickly. This is indicating the three models I constructed. To construct these models, I proceeded through three phases of analysis. I mentioned the task-based clinical interviews. There were 12 of those. that lasted the majority of the teacher's, most of the second semester of his pre-calculus course. In this second phase, I conducted pre-lesson interviews to get a sense for the mathematical knowledge the teacher leveraged to design lessons and assessments, and also did classroom observations. I incorporated teacher journaling, where I would send the teacher questions and prompts electronically every day after the lesson to get at his rationale for what seemed to be consequential instructional choices. And for these journal prompts, I selected prompts that fit into one of three categories. The primary one was to elicit the teacher's justification for moments when his enacted mathematical knowledge differed from my model of his personal mathematical meanings, to get a sense for what are the potential environmental influences he's accommodating for. Is he being sensitive to students' affect? What are the things that might be accounting for these discrepancies? This is kind of giving you a sense for the chronology of how I analyze the data. There was a phase of preliminary analysis that occurred after this initial interview I conducted to get a sense of the teacher's mathematical meanings. Part of this resembles the structure of a teaching experiment methodology, where there's an initial interview where you're developing provisional hypotheses about an individual's personal meanings. And then all of this data collection here occurred simultaneously. The series of task-based clinical interviews were conducted throughout the teacher's instruction. Of course, there were the pre-lesson interviews, the classroom observations, and the journaling was a way for me to pursue hypotheses that were emerging from my ongoing analysis. This was followed by a phase of post-analysis that lasted about 9 months. And then I won't talk about this third phase here very much in this talk. But in this phase, I selected moments of the teacher's instruction and moments of the task-based interviews where the teacher, from my perspective, was conveying or emphasizing different mathematical meanings. And I asked the teacher to describe the meanings that he demonstrated in each clip and to compare them. I'll mention later on that the teacher didn't recognize any differences. So as far as the theoretical background, I approached this study and all of my work from a Piagetian perspective. I make heavy use of Piaget's genetic epistemology, including ideas of scheme, assimilation, accommodation, equilibration, and particularly different forms of abstraction. Piagetian abstraction and its 5 varieties were very consequential to how I analyzed the study's data, and they were obviously consequential to its results. So I'll take a second and just define how I think about some of these forms of abstraction. Here are 4 of the 5 forms of abstraction. There's meta-reflection, which I won't talk about. I'm only going to spend some time talking about reflecting and reflected abstraction. The term reflective abstraction, you'll notice, isn't here. That's sort of an umbrella term that encompasses both reflecting and reflected abstraction. And the use of reflective abstraction is a term that often precedes the publication of the 2001 translation of Studies in Reflecting Abstraction, where the translator introduced this distinction between these 2 forms of abstraction. So reflecting abstraction involves an individual engaged in an action to produce an effect. This action can be mental action, can be physical action. Piaget actually defined the kinds of action that he was thinking. It's any movement, thought, or emotion that responds to a need. So it's a pretty general definition of action. Reflecting abstraction requires the individual to differentiate the action from the effect it produces. So to dissociate the effect from the action, and to focus on the action as its own entity. The second sort of phase that's involved in reflecting abstraction is to what Piaget called project the action from the level of activity or the level of material action to the reflected level or the level of representation. This is constructing an internalized representation of the action dissociated from the effect it produces. And it's at this higher level, this level of cognition, that these internalized actions are organized with other actions to form schemes. And there are particular properties of these actions that allow them to be called operations, and that they're reversible and other sorts of things. So mental actions and mental operations are still they're all mental actions, but some mental operations have some other properties that are a bit more sophisticated. Reflected abstraction is an abstraction on the products of the results of prior reflecting abstractions. It's an abstraction on internalized actions that result from prior reflecting abstractions. And this involves operating on the actions, performing operations on them, that result from prior reflecting abstractions at this level of thought, which results in a coherence of actions. And the important part of reflected abstraction is that through this process, an individual achieves awareness of the contents of his or her schemes. This is the process by which individuals become aware, not just of what they're capable of doing, but how they think. And what's interesting about this distinction is it suggests that a conscious awareness of the contents of one's schemes doesn't come for free upon having constructed them. It requires an additional form of abstraction. The reason why this results in a conscious awareness is that for an individual to be purposefully operating on mental actions necessarily brings those actions into awareness. So this is where the conscious awareness comes. So I want to talk about the findings of this study rather briefly, but in 4 parts. Through the series of task-based clinical interviews, I recognized that the participant possessed 2 ways of thinking about a lot of ideas, angle measure in particular. I'm only going to talk about angle measure here, but he possessed at least 2 ways of thinking about sine and cosine values and sine and cosine functions, and at least 2 ways of thinking about the periodicity of these functions and what it means to think about periodicity, either constant or variant. So I hope we can hear this. Before I show some of this data, I picked a couple of clips that illustrate the distinction between the meanings that this individual had constructed. I'll emphasize that David repeatedly demonstrated these 2 schemes, these 2 ways of understanding. And so these clips are representative of many, many other instances in which he demonstrated these 2 ways of thinking. This is either going to be very loud or not loud enough.
What's approximately the measure of your angle in radians? What would you say?
2 5/3.
He's looking at a screen with that on it.
Why is that?
Because it's about 1/3 of the circle. And so the entire circle of radians would be 2 pi. So it's 1/3 of 2 pi, which is 2/3.
So David reasons about the fraction of the circle circumference this angle subtends. He's aware of the fact that there are 2 pi, as he uses, radians in a circle, and therefore the measure of this angle must be 1/3 of 2 pi. So a summary of this first way of understanding is to conceptualize an angle with a circle of arbitrary size centered at its vertex, to attend to the multiplicative relationship between subtended arc length and circumference, and then to use that fraction as a way of determining angle measures in particular units. When he was talking about radians, the angle subtends S over C of the number of radians in a circle. He did something analogous with degrees, because there are 360 degrees in a circle, that's the phrase he would use. The angle subtends S over C of 360. What is important about this scheme is that it's necessarily non-quantitative. The resulting numerical value doesn't necessarily represent the measure of something in some unit. So S over C, or we say 1/3 of 2 pi, or 2 pi thirds, when prompted to explain what is that a measure of, what attribute and what's your unit of measure, David struggled to articulate that on many occasions. Immediately following that previous clip, I asked David another question. I should have mentioned that down here, I doubt you could read that. That says radius, subtended arc, and circumference. These are representations of the magnitudes in the diagram. Of course, the circumference is behind that the subtended arc there. So I pulled those out to focus his attention, or to perhaps aid in his reasoning about particular multiplicative relationships.
Okay. If you had the same question, if they ask you about what's the measure of your angle in radians, but this is what you saw, what would you say?
I would say it's about 2.
What's that?
Because there are about 2 radius lengths in the arc.
I was surprised that he didn't immediately say, I've just answered this question, it's 2 pi thirds, or 1/3 of 2 pi. Of course, by my removing the magnitude that represents the circumference, this certainly prompted to David that there might be another response here. But still, I didn't put that response in David's head. He had to interpret the picture that remained in a way that was quantitative. And so now, 2 represents the measure of something in some unit. 2 is the measure of the subtended arc length in units of the circle's radius. And this is a way of thinking that David demonstrated, again, on multiple occasions throughout the series of task-based clinical interviews. And what was somewhat stunning about this is that David didn't transition from thinking about angle measures as a multiplicative comparison between subtended arc length and circumference, and then shift to thinking about angle measures more quantitatively. It was sort of intermittent. He would go back and forth between these, and sometimes be unable to interpret solutions in one context in another, even when directly prompted to do so. Just a couple other instances where David leveraged the second way of understanding. I asked him to use the features of Geometer Sketchpad to construct an angle with a measure of 1.6 radians. If you're familiar with this program, there are many ways of doing this. And the methods that an individual might go through to do this could reflect a quantitative or non-quantitative understanding of what it means to measure an angle in radians. What David did is he constructed a ray extending horizontally, a circle centered at its endpoint, measured the radius, measured a subtended arc length, and moved the terminal point, moved the terminal ray so that the subtended arc length was 1.6 times as large as the length of the radius. I would ask him questions like, what does it mean to say an angle has a measure of 3.92 radians? He talked about length of the subtended arc being 3.92 times as large as the radius. When prompted to actually physically construct an angle with a measure of 1.2 radians, he measured out string, iterated it along a circle circumference, that sort of thing. These are all instances of demonstrating this quantitative understanding of angle measure. This is not an understanding that necessarily reveals the idea of the circle itself being, the measure of the angle being an equivalence class of arc lengths. The way David conceptualized the circle was as an arbitrary circle. So any specific circle was for him a representation of a generic circle. And so there was this element of an equivalence class of arc lengths without that really being made explicit in his thinking. Okay, I've said enough about scheme B. So he clearly demonstrated these 2 meanings. He was incapable in some moments of reasoning in both ways or reasoning flexibly between them when thinking about particular tasks. It was clear to me that, I'll show you one of these tasks now, that he hadn't coordinated these meanings into a coherent structure, that these meanings weren't implications of each other. Here's a question that I asked David one of the questions I asked David that revealed that these schemes were uncoordinated. Now, this occurred reasonably late in the series of interviews, and so I was surprised, given how simple this task is, that David struggled. The question is, an angle has a circle of radius 1.4 inches centered at its vertex. The angle subtends an arc that's 5.3 inches. What's the measure of the angle in radians?
Suppose an angle has a circle of radius 1.4 inches centered at its vertex, and suppose the angle subtends an arc of 5.3 inches. What's the measure of the angle in radians? So the radius was 1.4 inches. And the angle subtends an arc length of 5.3 inches. And we want to know what the measure of this angle is in radians.
Okay. so circumference would be 2 pi times 1.4. And the arc length then is 5.3, so 5.3 is 2 pi times 0.4. That is the ratio to circumference. So
Okay.
So what's the measure of the angle?
it's about 0.6 radians.
So we notice here that, of course, the measure of the angle in radians is the length of the subtended arc measured in units of the circle's radius. What David did was immediately focused on the multiplicatively comparing the length of the subtended arc with the circle's circumference, and claimed that the measure of the angle was 0.602 radians. After a few minutes sitting quietly and thinking about this, I asked him, I said, "You seem dissatisfied with that." He said, "Well, I know that if the subtended arc length is 5.3 inches, that's going to be more than half the circle, and an angle that subtends more than half a circle has a measure of more than pi, and 0.602 is much smaller than that. This can't be right." So after a few minutes, he ended up crossing out his work and writing this, 5.3 divided by 1.4. And then I asked him, why is it 5.3 divided by 1.4? He said, well, what I calculated here was the fraction of the circle's circumference subtended by the angle. What I forgot to do, because there are 2 pi radians in a circle, I forgot to multiply that by 2 pi. And he says, so then your 2 pi's cancel, and you're left with 5.3 divided by 1.4. And I followed that up by asking David, is it possible that if an individual just wrote 5.3 divided by 1.4 in response to this question, suppose a student did this, how might he or she be thinking about what it means to measure an angle in radians? And he said, well, they've mentally canceled the 2 pi's. That's what they've done. Is there any other possible way of reasoning, this way of thinking that the student might have when responding to this question? If this is all they write, he said the only way of doing this is to mentally cancel the 2 pi's. That's what they did. This is stunning after having gone through many tasks in which he demonstrated an understanding of angle measure as the length of a subtended arc measured in units of a circle's radius. So my interpretation was that David possessed these 2 schemes, these 2 meanings for what it means to measure an angle in radians. And that in this case, he assimilated this task to one that just wasn't productive. And because he hadn't made a connection between these schemes, he seemed unable to interpret 5.3 divided by 1.4 as a quantitative operation, as a representation of the measure of something in some unit. I'll also mention that we're trying to understand why he leveraged these different meanings in different contexts, sort of sporadically. I tried to analyze the characteristics of particular tasks that he was answering to determine, is there something about this task that's eliciting scheme A? Is there something about this task that's compelling him to assimilate this particular question to one of his meanings rather than the other? And I couldn't find anything that was, in terms of the characteristic of the task, that would have led him to assimilate any particular task to one of these schemes. I often ask essentially equivalent tasks or identical tasks on different days, and he assimilated these tasks to different schemes. So then, as I mentioned, I observed David's instruction and I characterized the meanings that he was promoting or conveying in his instruction. A couple of examples. During the first lesson, this is a school that does a modified block system, which you probably know what that means. They have a long 1.5-hour class period 1 day a week, and Monday, Tuesday, normal classes all day, Wednesday, Thursday block periods, Friday normal, that sort of thing. The first class was an hour and a half class, and at the end of it, a student, I'd been observing this class for some time, a student who was sitting close to me, on the way out, he said, "I just don't understand what we're measuring," was his statement. "I don't understand what we're measuring." And perhaps you'll see why. He started his instruction of angle measure by identifying the thing that's, by trying to focus students' attention on the attribute being measured as the curriculum that he was using promoted. He asked students, when we measure an angle, what are we measuring? He talked a lot about, are we measuring the openness? Are we measuring the space between the rays? Are we measuring an amount of rotation? What does that mean to operationalize amount of rotation? Then he said, oops, wrong button. So it's not like we're measuring a length, right? How would we describe the thing that I'm measuring when we look at these angles? Student says the openness. He says, yeah, it's weird. How do you measure openness? We're not measuring a length. We have to think about what we're actually measuring. As Dr. Moore's extensive research on angle measures demonstrated, angle measures are classes of subtended arc lengths, measured in a unit that varies proportionally with the circumference of the circle that contains each subtended arc. That's what an angle measure conveys. If you can reduce that to an amount of openness, but when you operationalize what the numerical values represent, they're fundamentally arc lengths. So then David asked his students in the same lesson, what does it mean for two angles to have the same measure? And after some discussion, he guided students to recognize that two angles have the same measure if circles of equal radii centered at their vertex, each vertex, if they subtend the same arc length. That's what it means for two angles to have the same measure. So before he's talking about, we're not measuring lengths. What does it mean for two angles to have the same measure? They subtend the same length. He drew an image like this on the board and talked about the measure of the angle being 1/8. And asked students, why don't the units matter here? Why is it okay to talk about this angle as having a measure of 1/8 with no units? Students really struggled. This is about a 20, 30-minute conversation. And he said, well, if the angle subtends 1/8 of the circumference, we could say that maybe the circumference is 16 inches and the angle subtends 2 inches. What happens when we do our division? The inches cancel and we're left with 1/8. This 1/8 is not the measure of something. In this case, David is not promoting a meaning of angle measure as the length of the subtended arc measured in units of the circle's circumference. So 1/8 is a subtended arc length measured in an entire circumference. He was promoting here a unitless understanding of angle measure. Of course, if radians and degrees and other units of angle measure convey length of subtended arcs, I know it's popular for people to argue that angle measures are unitless quantities. To conceptualize them quantitatively in a way that's productive, they're not unitless quantities. He also reiterated, measure the angle as 1/8. I'm not measuring length. The measure of the angle is without units. In the curriculum that David was using, the text introduces these sort of fictitious units of angle measure to focus students' attention on the criterion that a unit of angle measure has to satisfy, and that its magnitude has to be proportionally related to the circumference of the circle that contains the subtended arc. So these quips and marks were sort of these fictitious units of angle measure, each of which was proportional to the circumference of the circle. And in talking about these units, David explained that an angle with a measure of 6 marks subtends 6/20ths of a circle's circumference. This is how he talked about it. This is a meaning that was sort of not quite what the curriculum was trying to promote. This is consistent with David's first way of understanding angle measure. If he was reasoning about this as the measure of a particular quantity, then to say an angle has a measure of 6 marks means it subtends, the length of the arc, of the subtended arc, has a measure of 6 in units of 1/20th of the circle's circumference. So again, the attribute being measured as subtended arc length, the unit of measure, is 1/20th, or a fractional part of the circle's circumference. So there's a quantitative meaning. This is more consistent with his second way of understanding. This is perhaps the most revealing instance from David's instruction where he conflated, or he leveraged one of his meanings for angle measure that was absolutely not productive for the task at hand. So here, I don't know if you can read that. An angle of a measure with a measure of 0.45 radians. It has 3 circles centered at its vertex of radii 2 inches, 2.4 inches, and 2.9 inches respectively. What was the question here? Oh, what's the length of each subtended arc? Yeah, what's the length of each subtended arc? So David said, what do angle measures tell me? We've been talking about this for 3 days. The portion of the circle. So what does it mean when I say 0.45 radians? How much of the circle do I have? I take 0.45 and I do what? So he walked students through this exercise. They weren't working on this independently. He wrote this on the board. He said, well, 0.45 over 2 pi, I first have to calculate the portion of the circle, multiply that by my circumference, because the arc length is equal to that fraction of the circle's circumference. Of course, this task was designed to support students' understanding of radians as subtended arc length measured in units of a radius, and to construct that quantitative relationship. Another instance, what does it mean for an angle to have a measure of 1 radian? This is a question that was asked in the text. A student said, well, it's about 1/6 of a circle. And I was surprised when David wasn't satisfied with this explanation, considering how consistent it was with his emphasis on angle measures as conveying a fractional part of a circle's circumference. The student said, it subtends 1/6 of the circle. And he said, no, it's 1 radian is 1 radius length of arc. So he's promoting these different meanings and not doing it in a way that's supporting students' understanding of angle measure as the length of a subtended arc measured in a particular unit. So this is, again, just a subset of the moments of David's instruction that were inconsistent in terms of the meanings of angle measure he was promoting. And the way I interpret this is that in the context of classroom teaching, students were asking questions and they were discussing particular tasks that they were working on in groups, and David was having to respond to these stimuli in the context of his classroom practice. And he was assimilating some stimuli to one of his schemes, which produced observable products, which he was enacting knowledge that was consistent with one of his angle measure schemes. And in other moments, he produced observable products of his other scheme. And so he was enacting knowledge that reflected, of course, the schemes that he had. This isn't surprising, of course. What was surprising is that the knowledge a teacher leverages in the context of instruction is not solely a consequence of having to respond to spontaneous things that arise. David planned his instruction. There was something deliberate about what he intended to do. And there were all sorts of inconsistencies, not just with respect to angle measure, but with respect to sine and cosine, and period, and graphical representations, and other things. And that in his planning, he didn't seem to notice some of these issues. He didn't seem to notice that some of these things were problematic, or that he might be conveying meanings that were potentially compatible, but he didn't support students in actually making those connections. So I said that I'm not really getting into the third phase of data analysis. I did mention that I collected these pairs of videos from the clinical context and the classroom context that, for me, really demonstrated very different meanings for angle measure, sine, cosine, and other things. And this third phase of interviews was I asked David to watch each segment of instruction, to explain, to describe the meaning that he promotes in each, to see if he's interpreting each video in the way that I interpreted it, and more importantly, to identify whether or not the meanings he's promoted are consistent or inconsistent. Every single pair of videos that he watched, and there were 9 in total, David claimed to be conveying the exact same meaning. In these interviews, I tried to get at how is he seeing these as being the same? And through those interviews, this raised my awareness to an important distinction that I think has implications for how teachers leverage their mathematical knowledge to achieve their instructional goals and objectives. There is a distinction between a teacher being consciously aware of the products of his or her schemes, the solutions they're capable of obtaining, the problems they're capable of solving, versus the contents of the schemes themselves. So this diagram here is Pat Thompson's Didactic Triad. A teacher's awareness only of the products of his schemes, and by products I mean David, in this third phase of interviews, would explain the meaning I'm promoting in these clips are the same because I achieve the same numerical result. The answer is the same. The result is the same, so they're the same. And I tried to get at, are there any ways in which he might see these as being different? I provided as many opportunities as I could for David to justify how the meanings he's promoting in the clinical and classroom context might differ. And he didn't notice it, even when I was trying to focus on not just the products. His focus was entirely on what his enactment of his knowledge allowed him to do or allowed him to convey, not the contents themselves. And so this had implications for how David defined his instructional goals, for how he designed and selected materials, for how he interacted with students, for how he conceptualized how a class would unfold, and so on. I mentioned that this way of operating, this way of enacting knowledge to achieve goals that are informed by a teacher's awareness of the products of his or her schemes differs from being aware of the organization of mental actions and operations that comprise the meanings themselves. And as I'll argue in a minute, that kind of awareness is essential for enacting instruction that has the potential of really informing or of advancing students' understanding. So quickly, it seemed to me that David hadn't sufficiently engaged in reflected abstraction to become consciously aware of the contents of his mathematical schemes. So I tried it through the task-based interviews. This was sort of nearing the end of his instruction of these ideas. I tried to design tasks and experiences that would promote this reflected abstraction, would provide opportunities for David to perform operations on his own mental actions that comprise both scheme A and scheme B, so that he might bring them into awareness. This is one task that I designed for this purpose. So here Nick claims that the measure of the angle is 3/8, and Megan claims that the measure of the angle is 3. How might Nick and Megan be thinking about measuring the angle? So this task is designed to focus David's attention on, well, first of all, Nick and Megan reflect David's two schemes. So, here, how are they thinking about measuring the angle? He was able to describe that. I designed this task to focus David's attention on a thing being measured in a unit of measure, and that both 3 and 3/8 can be the measure of this angle, but what's different about this is the unit that Nick and Megan are using to measure the length of the subtended arc. This is a non-trivial task for David, but ultimately he was able to answer this, and he was able to explain that both Nick and Megan are measuring the same thing, they're just measuring it in different units. And he said, if Nick's thinking of 3/8, if he's thinking of it as 3/8, then he's thinking of 3/8 of the whole, so his unit of measure is not the red dots, his unit of measure is the whole circumference. Megan is saying that it's 3 units of measure where 8 make up the whole, and she is saying that it's 3/8 of the whole. So they're measuring the same thing, but they're using different units. This is David's statement. I also engaged David in a task where I sort of represented to him representations of my interpretation of his schemes. And I asked him to compare them, to think about them. The comparison was the operation on the meanings that he seemed to be demonstrating. So Courtney claims that the measure of the angle, Courtney claims that measuring an angle in radians means measuring the arc length that the angle subtends in units of the radius of the circle centered at the angle's vertex. Rebecca says that to measure an angle in radians, you take the length of the arc that the angle subtends, divided by the length of the circumference of the circle, centered at the vertex of the angle, and then multiply by 2 pi. Are they both correct? I was stunned that he said no, they're not correct. That was his immediate reaction. He said they are not both correct. Ultimately, David was, after a few minutes, he drew pictures, he represented them. He realized that numerically, with specific examples, they are both correct. We returned to this task, the task from the series of task-based interviews, where he struggled to conceptualize 5.3 divided by 1.4 as the measure of the subtended arc in units of the arc's radius. Upon examining his solution to this, a light bulb went off. He said, I was thinking about this in the way that Rebecca was thinking about this. I should have been thinking the way Courtney was thinking about this.
So then here, when you came up with 3.785, you just divided 5.3, which was the length of the subtended arc, and 1.4, which was the length of these radius. So why did you do the division?
Well, because again, here I said that really I realized I needed to take this and multiply it by 2 pi. So if I just remove that from the problem that we get in. And when we're measuring in radians, what we're doing is we're saying that it's 1 radius length. So really I should be thinking about how 1 radius goes into 5.3 instead of how 5.3 goes into the circumference. That was the difference in my thinking. So up here in this one, I was thinking more of what percentage it was of the circle instead of just doing it the easy way and saying how many radians are going to actually be in here, where a radian is that length. So how many times does 1.4 inches go into 5.3?
Okay.
Which is what I should have done.
So after this and a few other tasks that I designed to engender a reflective abstraction, I revisited the tasks that David struggled with during the series of task-based interviews in terms of interpreting his solutions, both in terms of the meanings he demonstrated to his 2 meetings. We returned to these tasks so I could see, is he reasoning about these ideas more fluently now? And he was much more capable of interpreting his solutions in terms of both quantitatively and sort of his whole thinking, as he liked to explain. So I mentioned at the beginning that a sort of hypothesis emerged from this work, and that hypothesis is the essential role that a conscious awareness of the contents of one's schemes has for effective teaching and as a component of the knowledge base required for effective teaching. So this is my image for pedagogical content knowledge. And PCK is defined many different ways in the literature. One question that's often not addressed is what makes pedagogical content knowledge pedagogical? So, of course, effective teaching requires strong subject matter knowledge. In my view, teachers also need to be consciously aware of the contents of the schemes that they want students to construct, and that their instruction hopefully is designed to support students in constructing. For me, this duality constitutes mathematical content knowledge for teaching. Together with an awareness of epistemic ways of understanding how students are typically reason about mathematical ideas and leveraging that to inform their instruction, with an explicit way of thinking about what mathematical knowledge is and how it develops, this constitutes my image of pedagogical content knowledge. What's a bit different about this is that pedagogical content knowledge, at least as I've conceptualized it through this work, isn't a kind of synthesis of pedagogical knowledge and content knowledge. What makes pedagogical content knowledge pedagogical are the ways in which this awareness of mental processes enables a teacher to act in pedagogically effective ways. So I hypothesize that this awareness informs how teachers design and select curriculum materials, how they employ pedagogical actions in the moment of teaching. It provides, in a way, a disposition or an incentive to attend to students' mathematical thinking. Teachers can't attend to students' thinking if their objective isn't to really influence students' thinking. If their objective is to influence students' behavior, then there's really no incentive to think about or to construct models of how students are thinking and to leverage that in their instruction. I hypothesize that this kind of awareness provides a sort of necessity to do that. And, of course, defining instructional goals and objectives. A teacher can't define as a goal of his or her instruction intended mental states if they're not aware of the mental states that their instruction seeks to achieve or to support. This is a part I didn't talk at all about. But there was a part of the study with David that suggested that this lack of awareness of mental processes also influenced how he appraised aspects of his environmental context, including sort of external circumstances and his own mathematical knowledge, his affective characteristics, and the intellectual and affective tendencies of his students. I mentioned pedagogical content knowledge, and of course there are many conceptualizations of it. Often it's a component of a more general framework for mathematical knowledge for teaching. But in these frameworks, the knowledge base required for effective teaching is in some way a synthesis of mathematical knowledge and pedagogical knowledge. see this reflected in, this is only a few of them. There are many more. In fact, there was a meta-analysis published in 2013, I believe in JMB. And one of the main results of this meta-analysis of the PCK literature was that this term is used in many ways, it's defined in many ways, but if there's one thing that we agree on, it's that PCK connects at least two different forms of knowledge, content knowledge and pedagogical knowledge. And this is a way of thinking about PCK that this study with David has compelled me to question a little bit and to begin pursuing in what ways is pedagogical knowledge not really a synthesis of these two different knowledge domains, but in what ways PCK mathematical knowledge with characteristics that endow that knowledge with pedagogical affordances or pedagogical utility. And I'm interested in understanding what are those characteristics of a teacher's mathematical knowledge. Is a conscious awareness of the contents of one's schemes one of those? If so, what are its effects? Are there other characteristics of an individual's mathematical knowledge that have pedagogical implications, and what are they? So I tried to stay at 45 minutes, which I think I'm slightly over, and I certainly appreciate your attention.
Open the floor for questions now.
Dr. Yu.
After this final discussion about how many 1.4s are in 5.3, did David alter his view about measuring angles as being about measuring lengths?
Mm-hmm.
Because he said in some of the quotes you were showing us that it was not about measuring lengths.
That was from his instruction. I can't say with certainty that his perspective was altered. I would be more comfortable saying that his schemes were coordinated and he was more capable of reasoning flexibly kind of between them. I don't know if there was a complete shift in his conception of angle measure as being exclusively about or conveying information exclusively about subtended arc lengths.
Wouldn't expect it to be exclusively about, I guess the question, the way I would phrase the question is whether or not sort of measuring in lengths was sort of prioritized.
Oh, in his teaching?
No, for himself, sorry. I wouldn't think of these other ways of thinking to sort of displays, sort of how that sort of sketch of trajectory of emerging competence or that sort of notion of comparing lines how become sort of over time, sort of more the central way to think about it.
That's a good question. I didn't collect the data to actually to really address that. My hypothesis is that he seemed to, just based on the way he reasoned about tasks that I reintroduced. The second, more quantitative way of understanding was more dominant in his thinking, but I was focused in those tasks on identifying the extent to which he could interpret his prior solutions in both a quantitative and sort of whole ways he talked about it. One of the things that was unfortunate was that by the time we concluded these phase 3 interviews and readdressed some of these tasks, David had concluded his instruction of trigonometry in general, and so I was very interested I wish I had the opportunity of seeing how his instruction might have shifted. I didn't have that opportunity after that. It's one of the things I'm working on now. I've designed an instructional sequence for constant rate of change and linearity, and I've implemented that with student teachers at Oklahoma State. The design principle for these task sequences is engendering reflected abstraction, and I'm currently in the process of examining these teachers' instruction now that they are in-service teachers, and some of the results are promising in the sense that it seems to have had an effect. Of course, I don't have any information about the quality of their instruction prior, but as far as David's, in the extent to which he shifted or began to adopt, this quantitative way of understanding, I don't know if I have enough data to really support that. Yes.
I'm wondering, and kind of building on what Andrew was asking about, even at the end, where he's measuring the 5.3 by 1.4 or whatever the numbers were, it's possible that he's still kind of in the background, that 2 pi is still lurking in there. And even in your scheme B, I'm wondering if even when he does describe a length in terms of the radian, or the radius, that he's still kind of almost taking that 2 pi into consideration. He's kind of going back to the unit circle in some sense. And so part of what I'm wondering is, when you're, I think when you're talking about this quantitative view, you're kind of, and you're talking about measuring things in terms of the radius, implicit in that is that the radius itself is a variable part.
Mm-hmm.
It is a part whose size itself can vary. And being able to measure something in terms of something that varies, I mean, that's not a common thing that we do and talk about. I think it should be.
Yeah, no, that's a really.
How did I know that was
You won't be
gonna happen?
surprised. But I'm wondering if maybe, even when you describe that scheme B, you might be perhaps attributing more to him than he really has. In other words, he still may not see that in terms of a variable radius. It may kind of, built into it might still be that unit circle, and so those really aren't so different in some ways. I don't know, I'm just wondering.
That's a great question. The idea of a variable radius, I think that it's possible to conceptualize. Dr. Moore might disagree with me. In a way, I hope so. I think it's possible to conceptualize angle measure quantitatively if an individual conceptualizes the circle centered at an angle's vertex as a representation of all circles. And that in that case, a quantitative meaning doesn't depend on an image of the radius varying smoothly or continuous variation. One of the difficult things about designing learning trajectories for angle measure is knowing what to privilege when. So one of the things we want students to construct is the criterion that a unit of angle measure has to satisfy, and it's proportionality to the circumference of a circle. And proportionality isn't necessarily an invariant multiplicative relationship between things that vary. It doesn't make sense to say that 5/7 is 5 is proportional to 7. It's a characteristic of varying quantities. And so when you do that, one of the meanings you have to leverage is this sort of part-whole thinking to construct this criterion. But then an individual has to shift to thinking about angle measure as the measure of the subtended arc length with the expectation that the radius represents a varying quantity or an arbitrary quantity. And that learning trajectory has the potential to support an individual's understanding of angle measure non-quantitatively if you focus on the criterion that the unit of angle measure has to satisfy before getting into what an angle is measuring. But if you don't focus on what are the characteristics of the unit, how can you focus on what it means to measure an angle quantitatively? And so this is kind of, it's a difficult thing that I've run into with learning trajectories with angle measures. If you focus on a particular circle, well then the radius isn't varying. And so you're not thinking about angle measure as an equivalence class, and you're not attributing this really important characteristic of the unit of angle measure. And then it does co-vary with the magnitude of the thing being measured. And so I think your question is a good one. I think that the way David was thinking, and I believe that there's sufficient evidence to support this, is that the circle represented a generic circle. And that radius wasn't just that radius, it was all radii. And so that circle, and at one moment he told me, he said, well, I said something about if I change the size of the circle, what changes? He said, this circle is the same circle, whether or not I'm looking at it on this page or I'm looking at it from space and it's the size of Texas. That's what he told me. Which that idea sort of allowed him to reason without thinking about the radius as a varying quantity. But perhaps you have something to add to that.
Yeah, I think I would agree. No, I do agree with that. I think having intellectual need for a varying radius, that's not just states variation, right? Oh, here's a state, here's a state, here's a state, but thinking more smooth variation, that's difficult to actually generate intellectual need just in the context of angle measure, because you only need a generic circle to measure an angle. But where that is actually absolutely necessary is polar coordinates. So if you're thinking of relationships in polar coordinates, now you need to have the images of variation and understanding how that relates to angle measure. You think of plotting curves that are covariation in polar coordinates, and that is where intellectual need for that imagery can come up. That's just not stage generated.
But you won't even have that invariance. I mean, how do you even know that you're getting the same thing for all circles unless you already have that kind of dependence, proportional dependence on the length of the radius already?
Yeah, so I think, is
So
it proportional by
that has to
states,
be-
or does it actually entail smooth
I don't,
variation,
I don't know.
right? That I think.
I wasn't
it's-
talking about smooth necessarily, I was just saying, to be able to consider whole bunch of different arbitrary radii. To be able to measure in terms of radians, you have to work with that proportionality. That sort of has to be built in.
Yeah, and I'm saying what that proportionality looks like can be very different than the images and schemes students draw on.
Yeah, I'm
There
not
could
saying
be-
it have to be some sort of thinking about smooth there.
Right. You at least need different states.
That's a good question. Yes.
I would, a different kind of question, I think. Thinking about that last interview, and you said that David didn't see any differences in his conceptions while personally and his conceptions while teaching, right? Is that what you said?
Yes, and I also compared. So those are the main pairs that I assembled, and I also assembled sort of pairs that were both from the clinical context, pairs were both from teaching, and so in all of those he didn't.
He didn't see any. So did you happen to introduce this idea of his talking about length in his teaching versus any of his other work with angles in the clinical context?
Did I explicitly bring that up to him?
Mhm.
I didn't.
Okay.
No, I didn't. What might that have allowed me to do?
Well, I'm just wondering if his looking at his instruction when he's talking about this is not a length, this is not a length, this is not a length, and then later on when they're actually talking about it being a length, if that might allow him to reflect on the differences between those conceptions.
Yeah, I think I didn't consider doing that. That's a good point.
I have time for one more question. Are there any last questions? Great use of weight, Tom.
I'll just make one other comment about sort of the MKT piece in general. So I think the problem, sort of a main problem with the fall approach that you have there is that there's no genetic account. Right, so they sort of describe knowledge in these categories, but there's no explanation about how it can be built.
Right.
And I think that actually, sort of a side comment, I think that's why they're having a lot of trouble with the measures, is because they don't have a kind of a genetic account. So when they're trying to sort of develop measures, separate this category from that category, they can't. I think that signal that this stuff is coming from a simple, to be constructed out of like a common source and sort of not really acceptable. And sort of way that you can make that piece of tape for yourself that you showed on the last or second to last slide, because sort of a nice sort of response to sort of what that genesis might look like.
And I think that
I think that's a real contribution to that conversation that these two made.
I appreciate that. I think that Ball and Heather Hill's commitment to constructing a practice-based approach has contributed things about what might be different areas of practice that require the enactment of mathematical knowledge. But I've actually not considered, as you mentioned, the lack of genetic they haven't really taken a genetic approach to this, and I haven't considered how that might contribute to the difficulties they've experienced with developing measures for them. That's a really interesting point.
Yeah, we're out of time, so thank you for speaking.